All right, welcome back. So the other topic we need to talk about with this idea of forces in space, or 3D forces, is the idea that just like in 2D, what we can do with these vectors is we can add them together. Just like we saw before, if we add vectors together, we end up with some resultant force. We said that was equal to the sum of the sum of all the other forces. Last time, or earlier in the semester, we said that we could look in component form and say the resultant of the forces in the x direction is equal to sum of all the forces in the x, and the resultant in the y is equal to sum of all the forces in the y. Same idea here, except we're adding one more, saying resultant in the z is equal to sum of all the forces in the z direction. So let's take a look at an example on how we would use this addition of forces. So in this example, we have this bar OA that's being supported by cables AB and AC, and we're given that the tension in cable AB is 183 pounds. We're also given that the resultant of the force is along, got cut off, along the OA, along this bar that's sticking straight out. What that means is that the resultant force pulling it either left or right along the z-axis has to be equal to 0, or sum of the forces in the z equals 0. We're asked to find the tension in cable AC. So in this case, I could draw somewhat of a free body diagram because we're given the tension of AB. So I have some kind of tension along here of 183 pounds. There could also, or there is, a tension of AC, and that's actually what we're looking for. That's what my free body diagram looks like. It ends up that it's irrelevant what our force P is. There's just a relationship between AB and AC because we are given that the force, sum of the forces in the z direction equals 0, and P, if you remember your components, would be all in the y direction. So the way that I would do this is I need to put these two vectors, these two forces, the 183 pound and the tension in AC, into component form. And to start off with, I'm going to find the length of each one of those cables. So starting with AB, and basically this is a proportionality of you know, the length in the x, y, and z direction for each cable. So for AB, I can see in the x direction, and I like to keep my signs in here to keep it straight. So how far do I get from A to B in the x direction? I can see that that's 48, but it has to go in the negative 48 direction, or negative x direction. So negative 48 squared, plus in the y direction, I'm going up a positive 29 inches, squared that. And then in the z direction, I'm going over a positive 24 inches. If I plug that in my calculator and end up with the total length of cable AB to be 61 inches. Same idea with cable AC. For AC in the x direction, I'm also going in negative 48 inches. For the y direction, I'm going up 25 inches. And in the z direction, I'm going negative 36 inches. Multiplying that through, I end up with the length of cable AC to be 65 inches. The reason I did that is now I can put it into component form based on what we saw with our notation, where I would say the tension in cable AB is equal to the total tension of AB, 183 pounds, times the distance in the x direction minus 48 over the total 61. So what I'm doing here, the reason I put my negative sign in here even though I'm squaring it, is when I'm visually doing this, I'm just saying, well, I'm taking each one of the components and then dividing it by the hypotenuse, and that would be my component in that direction. That all is in the x direction, or I hat direction. And then I have in the y, or j hat, I have 183 pounds times 29 over 61 j hat, and in the k hat, I'm also positive. I have 183 times 24 over 61 k hat. Multiplying that through, what I end up with is a negative 144 pounds in the I hat direction, a positive 87 pounds in the j hat direction, and a positive 72 pounds in the k hat direction. And next step would be to put the tension of AC into component form. Even though I don't know the magnitude of AC, I can still put it in component form by leaving in the variable. So instead of a value, I have tension of AC times the magnitude in the x direction is negative 48 over 65. So that's my I hat. Plus I have tension AC times 25 over 65 j hat. And then I have minus tension AC times 36 over 65 k hat. I'll just leave that in fractional form because after this, what I'm doing is I'm saying, well, what do I know about this problem? What I know is that the resultant force in the acting along OA has to be equal to 0, or some of the forces in the Z equals 0. Let's just jump up to that and say, well, I know that some of the forces in the Z direction must be equal to 0. Well, Z is my k hat, right? So my k hats have to sum up to 0. So we have 2 k hats from each vector. Basically, that has to equal 0. Probably should have put a line under the other one because I already have it calculated out. So with my k hats, I have the 72 pounds from my other unknown tension AC. Its component in the Z direction is 36 over 65. And that whole thing is equal to 0. From that, I can solve for the tension of AC and find that that's equal to 130 pounds. So the next section of this is going to be equilibrium in 3D, and all these problems will follow kind of the same process. So once again, you're taking the magnitude of any kind of forces that you know, you're breaking into component form by finding the length of the cable or the strut or the length at the, it basically is just given a directional component of each vector in the I, J, and K directions, and then you're adding everything up and summing it up to 0. So hope that made a little bit of sense, and I look forward to talking to you soon. Thanks.